Hello. In this video, I'd like to discuss a few applications of mean value theorem and also a few properties of derivative. So let me first remind you the mean value theorem that we're going to use. The mean value theorem, or MVT in short, and the F is for a continuous function defined on a closed interval. And this function is differentiable on an open interval. Then, okay, so we have a closed interval from A to B, and a function f is continuous and differentiable. Then, there is this point x in the open interval, okay, such that the instantaneous rate of change, or the derivative of this function, okay, the derivative of this function agrees with the mean rate of change, which can be computed by b minus f of a and b minus a. So this right hand side is simply the slope of the line segment that connect those 2 points. Okay, and mean value theorem tells us that there exists some point x, okay, x at which the tangent line has the slope that the slope is the same as the mean rate of change. Okay, and for this function, there are two candidates of such point. The same, the slope of the tangent line is the same as the mean rate of change. Okay, that's the mean value theorem, and we're going to apply this theorem to find a few properties. Let me first define a few terminologies. The monotonicity of the function. Let's say we have a domain of definition, which is the interval I, and function f is defined on this interval, a real valued function. We're going to say this function is increasing on the interval. Okay. If we have 2 points x1 and x2, both of them are points in the interval, and if x1, x2, these 2 points have the order relation like this. That implies the order relation between the corresponding value, f of x1 and f of x2. Okay. We're going to say the function f is increasing if we have this inequality. Okay. The order of the arguments or order of the independent variable will be preserved, but we allow the equality sign. Okay. And a decreasing function will be defined by the reversed inequality. In addition to that, we're going to define the strictly increasing function. Okay. I simply dropping the equality sign here. So for 2 points x and y, if x1 is less than x2, that implies the inequality between f of x1 and f of x2. These two values will satisfy the inequality like this. Okay, and similarly, we're going to define the strictly decreasing function by changing the direction of the inequality. Okay, and the derivative tells us the instantaneous rate of change, or the slope of the tangent line, that determines whether the function increase or decrease. Okay, so I the corollary, as a corollary of the mean value theorem, suppose we have a differentiable function on an open interval. If first we have two claims. If the derivative f prime of x is positive for all x, then the function f is increasing. Similarly, if the derivative is negative or non-positive, then the function is decreasing. And also, if we drop the equality in this condition, if the function has the strictly positive derivative for x, then the function f is strictly increasing. Again, if we have a negative sign for the derivative for all x, then the function is strictly decreasing. So the sign of the derivative determines whether the function increase or decrease. Okay, the proof of this property. I think all of you already know this property, but the actual proof relies on the mean value theorem. Let me just give you the proof for a second statement with a strictly positive sign. So let's assume the derivative of x is strictly positive for all x in the domain of the function. Then, to verify the strictly increasing property, we need 2 points x1 and x2. Okay, so let's consider x1 and x2. Okay, such that this x1 and 2 has this order relation, and all of those both of these points should belong to the interval from a to b. So x1 must be greater than a, and x2 must be smaller than b. So let's choose those 2 points and compare the value, the corresponding value, which can be obtained by the mean value theorem. With the mean value theorem, let's consider the mean rate of change on the interval from x1 to x2. So f of x2 minus f of x1 over x2 minus x1. Okay, this is the mean rate of change, just like this. And this one must be the same as f prime and x. Okay, for some x. Okay, between the interval from x1 to x2. Okay. Anyway, in this case, we assume the derivative is always positive, strictly positive. Okay, and this quantity x2 minus x1 is strictly positive, since x1 is smaller than x2. Okay, so the numerator should be positive too. F of x2 minus f of x1 must be positive, strictly positive. Okay, so we prove the strictly increasing property from the sign of the derivative. Now, what about the converse of that statement? Is it true? The question is suppose the function f is differentiable, interval from a to b, and function f is strictly increasing. Does it guarantee the derivative is strictly positive for all x? Is it true or not? The question, this question, also the answer is negative. When give you the counterexample, I think you can easily find the counterexample for this question. What is that? For example, f of x is x cubed. Then this one is a strictly increasing function. However, the derivative at that point is 0. Okay, this is strictly increasing, but derivative of x is 3x here. So I find 0 to be 0. So you cannot guarantee the strictly positiveness of the derivative. Okay, now let me define a few class of differentiable functions. Okay, I'm going to use CK. This is a collection of functions. Okay, and in this K, the superscript K, the case derivative. The case derivative of x exists. And this case derivative is continuous. Okay. The set of functions which satisfy these conditions are denoted by CK. Okay. Then, for example, C1 is the collection of functions that f prime of x exists and continuous. And what about C0? C0 is just a collection of functions. F itself is continuous. Okay, so C0 is simply the the set of all continuous functions. But C1 is a differentiable function. Okay, C1 is it's slightly different from the set of all differential functions. We assume the differentiability and the derivative f prime itself is again continuous. Okay, so it's a slightly stronger condition than the differentiability itself. Okay, so CK is a class of function, a set of functions which consists of all the functions whose case derivative exists and continuous. Why do we distinguish those differentiability, different level of differentiability? Okay, so the question is, let's compare, for example, C3 and C4. Okay, the set of this C3 denotes the set of all functions with the third derivative continuous. And C4 is the set of all functions whose fourth derivative is continuous. Then we have natural inclusion relation between these two sets. Okay, this is the set of all functions. We can compute fourth derivative. And this is the set of functions whose third derivative is continuous. And the question is, okay, this set inclusion is proper inclusion. Okay, that means there exists a function in this space, but that does not belong to this space. Okay, by using the diagram like this, this is C3 and this is C4. Okay, then can you find any function somewhere around here? Okay, so this function f, you can compute the third derivative, but whose fourth derivative does not exist. Can you construct any function like that? Okay, so the question is find a function in function f, a function f in C3, but not in C4. Can you come up with any idea? You can start with a non-differentiable function like this. Okay, so suppose this is g of x. G of x is the absolute value. This function is not differentiable at that point. Okay, and what about you take the integral? Integral. Okay, let's say this is g1 and g2 of x is the indefinite integral of g1 of x. Okay, which can be written as, okay, this is absolute value of x is either x or minus x, or positive and negative. Then the integral can also be described by the piecewise function. If x is positive, the integral of x will be x squared over 2. And if x is negative, we're going to have minus x squared over 2. So G2 now goes like the parabola in this direction and another parabola in this direction. Okay. Now let's pay attention to this function G2. G2, whose derivative is Z1. Okay. So this one belongs to C1. You can apply the derivative of this function, and the derivative itself, C1, is continuous. Okay, but you cannot apply one more derivative. Okay, since d1 is not differentiable, this function g2 is not in C2. Okay. Similarly, by integrating this function one more time, okay, g3 of x is the integral of g2 of x. Now J3 belongs to C2, but not in C3. Okay, similarly, by taking the successive integration, you can easily find the function f like this. Okay, F4, G4. X is another integral of G3 of x dx. Then this function is the function that we're going to find, f of x, that belongs to C3, but not in C4. Okay, this function, the third derivative is this function g1. Okay, you cannot take the derivative anymore. So this is not in C4. Okay, so we have a different level of differentiability. But this distinction is based on the differentiability, the existence of derivative, the existence of third derivative and fourth derivative. Okay, here we have not discussed the continuity of this function. Okay, so we have yet another question. Why do we assume the continuity of the derivative? Let's say D is the set of all functions whose derivative exists. This is not a very well used notation. Let me just use D for the class of function, class of differentiable function. Then you can compare this differentiable function and the C1 class. All the functions in C1 must be differentiable and the derivative should be continuous. So you have this natural that inclusion relation. Okay? But this inclusion is proper. That means you can find a differentiable function whose value that does not belong to C1. So the question is, find the function f that belongs to D, but function is not belong to C1. Or find the function f that is differentiable, but the derivative is not continuous. Can you come up with any counterexample or any example like that? A differentiable function, but whose derivative is not continuous. You may apply similar idea like this. Starting from a discontinuous function. Okay, you first choose a discontinuous function as the derivative, then apply the integral. Okay. This trial is not successful in the end, but let's choose f prime of x as a discontinuous function. Okay. For example, prime of x and is the function like either 0 or 1. We have x is negative, x is positive. So the function has 0 value up to here, and suddenly change the value to number 1 and goes like this. This is actually a very popular function, which is the name Heaviside function. Okay. So this is a discontinuous, typical discontinuous function. Then what if you take the integration f of x is the integral of this Heaviside? That's going to be, for negative x, you still have 0. For positive x, you're going to have the function x. That means the function has 0 value and the straight line like this. Okay. However, this function is not a differentiable function here. Okay? This is not differentiable. So this is not a proper example for this question. Actually, this kind of approach cannot be successful because the derivative function has the okay, we're not going to say the function, the derivative is always continuous. Since these two classes of functions are different. Okay, some function is differentiable, but whose derivative is not continuous. Okay. However, the derivative functions has a very its own important property. Although we do not know the continuity of the derivative, however, it has the intermediate value theorem as a conventional, as a general continuous function. Okay, all the continuous function has the intermediate value property. Or the intermediate value theorem. Okay, what's the intermediate value theorem? The function f is continuous. And continuous. Then, okay, suppose we have a closed interval from A to B. Then there exists point x in this interval. This interval. No. Here, f for any y0 between f of A and f of B. Okay, which means, hey, suppose you have a continuous function on the interval like this. This is f of A and f of B. Okay. For any intermediate value y0, the continuous function that connect those 2 points should pass through this value. Okay. There must be a point x. Okay. There exists point x, domain of definition, such that f of x realize this intermediate value. Okay. That's the intermediate value property or intermediate value theorem. A continuous function has the intermediate value property. Okay. Here, I have to prove the intermediate value theorem for derivatives. Okay. I'm not claiming that the derivative f prime is continuous. Okay. We do not know the continuity of the derivative in general. However, all the derivative must have the intermediate value property. Okay. This can be stated in this way. Say suppose you have differential function. Then x1, x2 is 2 points in the domain of definition, and instead of y0, let's choose c as the intermediate value. C is a value c lies between f of x1 and f of x2. No, actually f prime of x1 and f prime of x2. Since we're going to discuss the intermediate value property of the derivative. Okay, for differential function f prime, the derivative function has the intermediate value property, which means if you have 2 points x1 and x2 and an intermediate value c between f prime x1 and f prime x2, then there exists some point x between those two numbers x1 and x2 such that f prime and x realize this intermediate value c. Okay, this is the intermediate value theorem for the derivative. Again, I'd like to emphasize that this derivative f prime is not continuous. We do not know continuity. Okay, although we do not have the continuity, the derivative function has this kind of intermediate value property. Right? So C is the intermediate value. There are 2 different cases. Either f prime x1 is smaller than f prime x2, and the other way around. Here, we may assume one case f prime x1 is less than f prime and x2. Okay. The proof for the other case will be similar. So between those two values, we have the intermediate value c. Then let's define another function g of x as f of x minus c, or cx. Then by taking the derivative g prime at x1 and g prime at x2. If you compare to g prime, it's going to be f prime minus c. So if you evaluate this, the derivative of g at x1 is going to be f prime x1 minus c. That's negative. But this one, g prime at x2 is positive. Okay? Then this function g of x is continuous. Okay? You know the differentiable function is continuous. And this is also continuous function. Continuous on x1, x2. A continuous function on a closed interval should have the maximum and minimum. Okay? G is the minimum on this interval, closed interval from x1 to x2. And this minimum point, is denoted by x naught or x zero. At some point, a minimum point is denoted by x naught. That belongs to the interval from x1 and x2. Okay? So this one is continuous and the differentiable function. If this function has the interior minimum, then the derivative at that point must be zero. The derivative g prime must be zero. That means f prime at zero is c. And that's our conclusion for the intermediate values there. So what do we need to show? This x0 is not the endpoint. Okay. So we want to show this x0 is not the endpoint, different from x1, and x0 is different from x2. Okay. For x1, let's analyze g prime at x1. G prime at x1. This is the limit. If you express the limit as using its own definition. As y goes to x1, g of y minus g of x1 over y minus x1. And we know this derivative is negative. Okay, so in the domain of definition from A to B, we have 2 points, x1 and x2. Okay, so this is x1 and x2, a closed interval. We're going to discuss the closed interval from x1 and x2. Then, when you take the limit as y tends to x1, y, okay, this is both side limit. But if you consider the right side limit, your y is greater than x1. Your y is somewhere around here. Okay, this derivative is negative. That means the function g g of x is decreasing function at has a negative slope at point x1. Okay, so the tangent line goes down. The function decrease. Right? Since g of x decrease at x1, x1 is not a minimum. Right? This is the value of g decrease at that point. This x1 is not a minimum. And similarly, g prime at x2 then the limit as y tends to x2 and g of y minus g of x2 and y minus x2. This derivative is positive. That means this function has tangent line with the slope is positive. The function increases at that point. Okay? This g of x increase at x2. This x2 is not a minimum. Right? So the actual minimum must appear somewhere inside of the interval. So x1 is the interior point. Okay. So g of x is has the interior minimum point. Sure. A differentiable function has if the differential function has the interior minimum, the derivative must be 0. G prime and x naught, the derivative must be 0. And this derivative is the same as f prime x naught minus c. So this value realize the derivative of original function f realize the intermediate value c. Okay. So let's go back to the previous trial. Okay. We want to find the function f, which is differentiable, but the derivative is not continuous. We have to find such an example. And our trial was choice of the derivative f prime as the Heaviside function, which has the jump discontinuity like this. Okay. This function, the Heaviside function, does not have the intermediate value property. Okay, this function has no intermediate value property. Why? If we choose point x1 and x2 here, then f of x1, f prime of x1 is 0 here, f prime of x2 is number 1. However, it does not, for example, for the intermediate value 1/2, there is no corresponding x. They realize the intermediate value. The function just jump, change its value by a jump it has the jump discontinuity. So if a function has jump discontinuity, it does not satisfy the intermediate value property. Well, f prime may not be continuous, but f prime has the intermediate value problem. So with f prime cannot have without discontinuity. Okay, that's why this trial was not successful. Okay, then let's get back to this problem again. How can you find such an example of function which is differentiable, however, the derivative is not continuous? Actually, this is not an easy question. Let me construct the functions, sequence of functions like this. Let's first consider, okay, g of x is sine 1 of x. If x is non-zero, since x is in at the denominator, you need to exclude the case like this. And if x is 0, we assign value 0. Then the graph of this function moves between -1 and 1. Okay? But this is not a sine x, sine 1 of x. So when x approaches to 0 from the right hand side, this argument goes to infinity. That means as you move, the point gets close to the origin, you have infinity many up and down behavior, I guess. And similarly, you have the up and down behavior, I guess. The factor of the y-axis. What has value 0? Now let's consider, let's say this is g1 and another function g2, which is, let's say this is g0 and another function g1. But if we multiply x to this function, x times sine 1. Again, we need to exclude the case when x is 0. And if x is 0, we simply assign value 0. Then, again, this function goes up and down between -1 and 1. But we have value x. Okay, so this is a bound, upper and lower bound of the function. Okay, the function g of x goes between x and minus. So the graph of this function starts this line and goes down like this, then goes up and down. This function g0 is not continuous at this point, right? That's not continuous. Since the right side limit does not exist and left side limit does not exist. So this is a discontinuous function, has the discontinuity at that point. But this one, g1, is continuous at every point. Right? The only problem occurs when x is 0. Okay? If x is different, x is not 0, this is very nice function. All the components are continuous. Okay? X is a continuous function. 1 over x is also a continuous function if you exclude the case and x is 0. And sine function is also a very nice continuous function. So this is continuous function, even if it is continuous at that point. Since the limit, the right hand side limit and the left hand side limit, all of them are 0. And the actual value is also 0. What about the differentiability? Is it differentiable? No, this is not differentiable. Okay. You can check. The C1 of x is not differentiable. However, our example, the answer to our question is actually function g2. Instead of x, now we're going to multiply x squared, sine 1 and 0. If x is different from 0, we have this expression, and if x is 0, you simply assign value 0. Now, this part again goes up and down between minus and 1. And the upper and lower bound is determined by this function, which is y is x squared, and the lower bound is y is minus x squared. Then the function goes up and down between those two parabolas. Okay, although it has very crazy behavior near the origin, just like this function has a chance to be differentiable because this function, the graph of this function is somehow squeezed by these two parabolas. The graph of this function gets flat at the origin. Okay. So let's check that this function is actually the answer to our question. For non-zero x, let's denote this function as f of x. F prime, the derivative. You can easily compute the derivative of this function away from the origin. So the derivative is simply 2x and sine 1 of x and plus x squared, and take the derivative of this function, the sine part, it's going to be cosine 1 of x. But you have to consider the derivative of this point, this harmonic function, which is minus x to the minus 2. Okay. So this is 2x times x sine 1 of x, and you have minus cosine 1 of x. And also, so the function f, this function is differentiable away from 0. Okay. In addition to that, you have to verify this function is differentiable at 0. So at x is 0, you have to compute the derivative of prime of 0. Can you just take the limit from this expression? No, we do not know the continuity of the derivative. Okay, so you have to compute this derivative using the original definition. Derivative of 0 is the limit as x tends to 0, f of x minus f0 divided by x minus 0. Okay, which is the limit. Here, f of 0, the value is defined as 0. So this is simply x squared and sine 1 over x divided by x, or x times sine 1 of x. That's this function g1. And this function, when you take the limit as x approaches to 0, the limit is 0. Okay, because this part is bounded in a closed interval from -1 to 1, and this x converted to 0. Okay, but f prime of x, the derivative if you take the limit of the derivative away from 0, the limit of 2x times sine 1 over x minus cosine 1 over x. This part converges to 0. However, what about this one? 1 over x diverges to infinity, and its cosine function oscillates between -1 and 1. Okay? So this one does not converge. So f is differentiable, right? It is differentiable all the points, including the point x, point 0. But the derivative of prime is not continuous. Okay? So this is very popular example in analysis, which is differentiable, but the derivative is not continuous. Okay. Now let me move to the next topic on the derivative of the inverse function. Here I is an open interval and n is defined on this interval 2r, which is 1 to 1 and continuous. And let's note the image of this function as j. Okay. Then, so this function f is 1 to 1. The function f from I to its image j is 1 to 1 and 1 to 2. Then we can construct the inverse function from j to r. Okay. In addition to that, we assume f is differentiable. If this function f is differentiable at some point x naught in the domain of definition, and the derivative is non-zero. Okay. So here we have an interval I, and have a 1 to 1 and 1 to function to its image j. This is function f. And we have a point x naught, and the derivative at that point is non-zero. Then we can construct the inverse function from j to I. Okay. The inverse function is obtained by simply taking the reflection with respect to this axis. So the inverse function goes like that. It's the reflection with respect to this line. It's going to be around here. Okay, so this is f prime, no, f inverse. F inverse. Okay. Then this point will be moved to that point. Yeah, and also the corresponding tangent line is located around there. Okay. Here, I'd like to claim f inverse. The derivative of f inverse at y naught. This y naught is the value of y. And y, the differentiability. This inverse is differentiable at y naught. Okay, that's f of x naught. So here we have x naught, and the corresponding value is y naught. And by taking the reflection, okay, this value is again y naught, and this value is x naught. Then the derivative at that point, derivative at y naught on the slope of the tangent line is actually the reciprocal of the derivative of original function. It's 1 over f prime x naught. Okay, fine. Okay, first, you know, the image J is open interval. This I is an open interval. Okay? And this function is one-to-one and continuous function, whose image must be an open interval too. Then we're going to compute the limit, the derivative at x naught. If the function f is differentiable at this point, so f prime at x naught, which is the limit as x tends to 0, f of x minus f of x naught divided by x minus x naught. Okay, we assume this value is non-zero. I'd like to take the reciprocal of this whole expression. Can you do that? The limit as x tends to 0. Can you take the reciprocal of this expression? X minus x naught divided by f of x minus f of x naught. It's the same as 1 over f prime x naught. Can you do that? Can you do that? To do that, the denominator, you have to pay attention to the denominator. This is possible because we have this expression together with the function f is 1-to-1. F of x is different from f of x naught. And it's different from x. Okay, if this is not 0, this is x naught. So if x is different from x naught, that's where we compute the limit. This value must be different because the function f is 1-to-1. Okay, for different value, for different argument, the corresponding value must be different. Okay, so we don't have any problem to take the reciprocal of this expression since the denominator is non-zero. Okay, and this value is also non-zero. Now, I'm going to translate this limit into the epsilon and vector scheme. So this limit can be understood as, or any epsilon, there will exist vector such that if x, the distance between x and x naught is smaller than delta, of course, it's not zero. This x is different from x naught, then this implies the difference between this quantity and this quantity, which is x minus x naught minus f of x minus f of x naught minus 1 over f prime and x naught. And this part converges to this value, the difference between those two quantities gets smaller than epsilon. Now that g is the inverse function. To distinguish that the f and its inverse, I'd like to introduce a new notation, g, for the inverse function. Then, this function g, or the inverse function, is also continuous. Continuous and y naught. Okay? Because the original function is continuous, it is inverse. The reflection with respect to the straight line, y equals to x, is also a continuous function. So using the continuity, there exists, instead of delta, I'm going to use new symbol, eta, a positive eta, such that if y gets close to y naught, this difference is smaller than eta, okay, that implies g of y and g of y naught. This difference, the difference between those two values, gets smaller. Okay? That means this one gets smaller than an arbitrary constant. Okay? We're going to fill this blank later. And this expression can also be written as g of y and minus. Since g is the inverse function, and this y is f of x naught, okay, then g of y naught recover the original point x. Okay. What if we choose delta for this blank? Then if y gets close to y naught, this difference is smaller than eta. That implies this difference gets smaller than delta. Then instead of x, I'm going to use g of y. Okay, instead of x, g of y, the difference between g of y and x gets smaller than delta. Then I can replace x, this x, by g of y in this estimation. I mean, instead of x, I'm going to use g of y minus x naught over f of g of y minus f x naught. This gets in difference minus 1 over f prime and x naught gets smaller than epsilon. And what about this? This is simply y, because g is the inverse function of x. Okay? And what about this g of x? Okay, again, correct. This is simply y. And what about this one? This is y naught. And moreover, this x naught can also be understood as g of y naught. Okay? That means the limit as y tends to y naught, g of y minus y naught, no, g of y minus g of y naught over y minus y naught. Okay, this limit approaches to 1 over f prime and x naught. Okay, and what is this? This is the derivative of g. This is g prime and y naught, or f inverse prime and y naught. Okay, so the derivative of inverse function is the reciprocal of the derivative of original function. Okay, that's the way to compute the derivative of an inverse function. All right. So in this video, we have discussed a few properties of the derivative and the derivative of inverse function, things like that. Okay, thank you.